Hello all, my name is Víctor Gómez and I'm going to present the advances of my thesis Improved Missing Helicon Plasma Thruster for its evolution towards a space application. For those of the program that don't know me, I'm Víctor again. I studied aerospace engineering, Ingeniería Aeronáutica in Universidad Politécnica de Madrid. Then I did a master's in autonomous vehicles dynamics and control in Cranfield University, and also I have studied an executive MBA in the EAA Business School, in addition to my current studies in the PhD. Also, I worked for CENER during 8 years, where I was working developing the helicon plasma thruster technology that we are going to discuss today. And also I worked for the Orbit last year, and now I'm moved as a contractor for AEC Clyde Space in Glasgow. The motivation for this thesis was born several years ago when CENER and EP2 decided to collaborate to develop helicon plasma sources as potential helicon plasma thrusters to be introduced into the electric propulsion space market. There we, when I was in CENER and the university started to collaborate, and then this thesis topic bloomed during several projects that we were developing together. The goals of the thesis are those indicated here. So basically we want to understand the limitations on this technology and in trying to improve it to a level that allows us to use it as a proper electrical propulsion system in space applications. The methodology that we have followed during the thesis development is based on experimental characterization of different prototypes that have evolved throughout the whole time of the thesis and the work that we have performed together with CENER, as a parallel action to the more industrialized action that is taking place there in CENER to get the full system. The idea here is to experimentally characterize and evaluate the performances of the thruster based on plasma analysis and thrust measurements, and get evolutions of the thruster or component modifications or structural designs that change the performance of the thruster and allows us to understand what is going on, what's happening, what is better, what's not, and that's a little bit the overall context of the thesis. As I mentioned before, this thesis is supported by mainly two projects that are related to industrial actions with CENER mainly. The first one was a GSTP program that was devoted to develop the thruster mainly from a prototype technology to a more advanced concept using permanent magnets. So the idea there was to develop the thruster. We were carrying out several experiments with some variable platform based on coils, and then we get out with an engineering model based on magnets. On that program as well, we were developing the electronics within CENER, but this is a separated action, but coordinated with the thruster development, which was part of the main core of the thesis evolution. Then the PATIA project arrived, which was a next step on the evolution of the thruster concept. The idea there was to evolve furthermore the thruster, verifying that it's able to perform for in-orbit applications, departing from intermediate TRL to an engineering model. The most important things of this project are the thruster itself, the development of the thruster itself, but also the characterization and analysis of the performance of the thruster and the impact on other subsystems like the propellant flow control system or the electronics, which are mainly tied to the thruster development and its behavior, as we will see later on. The first task that I was developing for the thesis was a system response analysis with the preliminary HPT-05M prototype that was the prototype developed together with CENER and the university group, based on coils. So basically we had like a plasma tube with some coils, and the first action that I take for the thesis was characterize this prototype with different input parameters like the magnetic field, mass flow and power, to understand how it will behave for two reasons. One reason was the characterizing the electrical response of the system, which could be an input for the electronics, but also for the understanding of how the plasma changes within the subsystem, within the thruster, and then get a experimental characterization of its behavior within different operating points, but also an input to the controller that we would like to implement in the future to have an autonomous system. Then the next step I took was related to the magnetic field generation within the prototype. So basically what I did was to retrieve different candidate configurations based on permanent magnets that could fit or could be similar to the one that we get with coiled, bearing in mind that the way the field is generated with permanent magnets is more different. We have like ASP within the domain and that sort of things, which complicate a lot the design here. But we try to keep more or less the same shape on the nozzle while retrieving more or less the same characteristical length on the prototypes and so on. So basically here what I did is outline two configurations. One which was based on small magnets that were tied together within a Teflon shape structure that we use to test several possible implementations, and then we retrieve a final configuration for the GSTP end part, which was the so-called HPT03. This was based on permanent magnets, fixed configuration. The only issue we had with this prototype is that the ignition was not possible directly to the point that we were expecting to have, because we were like at very high fields. Maybe the configuration within the elements was not correct, and that was causing problems. So we have to move forward from that point. Which brings us to the next step, where we consisted on retrieving several possible new configurations based on the initial ideas that we have for the HPT03, and change a little bit the magnetic field intensity that we had and the relative position of some of the objects, including also the antenna that was reviewed for that design. So basically we were playing here internally within the group to get different potential candidates for a thruster that could work. In this chapter, what I have included are like several attempts with different configurations, and we were retrieving a lot of data to be analyzed to consolidate a final new engineering model that will provide better performances than the ones that we observed with the HPT03M. Based on one of these prototypes, the Gandalf model, which was the one with the white Teflon structure, we were running a joint coupling test, which was required by PATIA, which allows us to analyze the whole system response, including the flow control unit and also the electronics in the loop. This enables us a couple of things. First, it was the first test that we will attempt with this system using the thrust balance, whose results are going to be shown a little bit later. But also it provides a lot of information about the system integration and possible ways of controlling it, which was also one of the projects that I had in mind for the thesis structure. We retrieve a lot of information of all the systems working together, and it also provides an important milestone in the project, demonstrating the functional change of the whole system. As part of this campaign, we also carried out a lot of tests related to thrust measurements. So basically, in this part of the thesis, I was focused on the results with the thruster that we have evolved from the coil one that we had before till this latest iteration, where we were more comfortable with the results that we were obtaining based on permanent magnets. Here come some of the results that we have. We had like two. We did these experiments with both the models that we had. Those are the results for the Gandalf one, which are mostly equal to those obtained with the variable magnetic assembly breadboard, or they were quite correlated. From those results, I have written the first paper that is pending publication. And here we can see that the performances of the thruster are quite poor. We are not above 2% of efficiency on thrust efficiency, which is quite poor, but we were able to retrieve several trends for different operational conditions, meaning different power conditions and different mass flow. And then my final contribution to the thesis is related to the control analysis that I did for the system. So basically, I have created a controller, which I have implemented and designed in Simulink, and also a preliminary design of sensorless control strategy, including the fluidics within the control, based on the response that we had during the system integration test. Then from those results, several implementations have been carried out by CENER, after all, including the controller within the electronics that has been demonstrated after I left the company. And also we were implementing certain configurations that we test with those models that I have already mentioned into the EQM, which is the model that you can see there and was manufactured also after I left the company. Here I have summarized again what has to be done for the thesis right now. So basically I have to release the first publication with the first prototype results, which is already finished and it's pending publication. We are being internally iterating and it has been in the fridge for quite a while. I have to push it harder. This is one of the points that I have to improve a lot. Then we would like to have at least one other publication because we have further results that we can further discuss, including some more proofs analysis with different prototypes, and also some thruster electronic response and control design results that we have already observed before I left the CENER. And then I have to write the thesis and finalize the whole work. Then to sum up, I have included here all the information, all the contributions I made during the thesis period. Basically, those contributions are mainly focused on the first years where I was more active and I was developing several contributions together also with the team on the different projects. And then in the latest years, I have contributed with some additional work related to the latest operation of the thruster, to the CNRS investigation on laser interferometry on the plasma plume of the thruster. Well, and this is it. I have tried to explain in some slides in a very short time all the work that I have performed within the thesis time regarding the thruster evolution, investigation, and further development. We have shown that the results that we have obtained with this thruster so far are not quite promising, but we have several theories on how it can be improved and how can evolve it through time. I have also contributed at system level with several contributions analyzing the response of the system and also implementing certain control features for the whole thruster control within the remaining parts of the system. And last but not least, I have to keep pushing on the writing part in order to finish as soon as possible the thesis and all the work that we have carried out. Thank you for your attention. Bye.